Okay, so for this talk, we're very happy to have Ahmed Alaoui from Cornell talk about computing extremal cuts in locally tree-like regular graphs. Thanks for coming.
Yeah, thank you very much, Christopher, for this invitation. Yeah, so I'll talk about some work that I've done with Andrea Montanari and Mark Selke. Andrea is at Stanford. Mark is now at the IAS, and he's going to Harvard afterwards. And this work is about computing combinatorial optimization problems on random regular graphs. And in particular here, not in particular, but perhaps a little bit more generally on tree-like regular graphs. And I'll explain what the notions of tree-like is and local is. Okay. Right, so I want to explain this notion of extremal cuts. And so, yeah, I have a graph V, G that is V comma E, which is a finite graph that is K-regular. And the vertex set is denoted by the set from of the integers from 1 to n. The maximum cut question asks you to partition the vertex set V into two sets, V plus and V minus, such that the number of edges that cross this partition is maximal. So that's the question. And one encoding of this problem into formulas, if I want to start writing formulas, is just to assign a plus or minus 1 to each vertex I, depending on whether they belong to V plus or V minus. And so the question becomes maximize this particular quadratic form where I sum over the number of edges, the number of edges that are crossed by this cut, okay, that cross the partition. And okay, so the decision variables here are these binary plus minus 1 variables sigma I, right? So this is the combinatorial optimization problem that is of interest. Another one that is of interest is somewhat the opposite of it, which is minimum bisection. And the question is to partition the set of vertices the same way. Here, I'm going to require as an additional, constraint that the partition be balanced. So the vertex sets V plus and V minus have the same size. And the edges, the number of edges that cross the partition is minimal now instead of being maximal. So you see, if I remove this constraint, the problem becomes trivial. So you can just put everything in one side and nothing in the other, and that gives you 0. But the problem becomes more interesting when you can put this constraint. You can also put the constraint here in a maximal cut. You can put the constraint that you want V plus and V minus to have the same size. That gives you another problem that is called maximum bisection. But they're morally equivalent in a certain sense, at least for random regular graphs. That's what it's believed. So let me just stick with this convention for now. Okay. Please stop me at any time if you don't understand anything. And of course, okay, so if you want to write it as a formula, you want to minimize this quadratic form. This is the number of edges that is crossed by the partition, or that is cut by the partition. And this constraint that the sides of the partition be the same size is encoded in this constraint. So here, let's just assume that n is even so that you don't have to worry about, if n is not even, this is either 0 or 1, and that's fine, okay? So these are the two main quantities that I'm going to be interested in throughout the talk. And for a worst case graph, these two quantities are intractable, computationally intractable. So there are results in computational complexity that tells you that computing these things is NP hard. So if you can solve them, you can solve any other NP hard problem. But in this talk, I will be interested only in a certain type of graphs that are called locally tree-like, regular as well. And I'll explain this notion of what locally tree-like is, but if you'd like, if you prefer, you can just think of random regular graphs. That's enough. Okay, so what is locally tree-like? So this is an epsilon delta kind of definition. So this is a finite graph G. I'm going to call it L comma epsilon locally tree-like if when I take a vertex I look at a ball of radius L around that vertex, I want it to be isomorphic to a tree. Okay, and I want this to happen for at least this many fraction, this many vertices. So if epsilon is 0, for instance, that means that all the vertices have a tree around them that is a ball of radius L that is a tree, and that is equivalent to saying that the graph has girth at least L, or 2L, I think, 2L. Okay. And an example of such graphs is, as I said, the random regular graph, G and K. And this graph satisfies this notion or this definition of being locally tree-like for all epsilon and all L, as long as n is larger than some constant that depends on both. Okay, fix L, fix epsilon, then if n is large enough, then your graph will satisfy this. And a lot more is known about these type of graphs. For instance, the girth is a logarithmic size. So as long as L is constant, n is large enough, then everything's fine. Okay. So if I restrict my attention to this type of graphs, I can still ask the same question of computing the maximum cut and the minimum bisection. Okay, and I want to do it efficiently, and I want to know whether this is possible or not. So that's the main question. So if you want to solve this question, I first want to understand what is the value that I should aim for. So what is the maximum? If I look at the class of locally tree-like regular graphs of certain degree, I want to understand what is the maximum and what is the minimum bisection, right? So that I have a value that I can aim for and try to bring algorithms and see whether I achieve that value or not. So let's look at the special case of random regular graphs and try to understand the asymptotic values of these numbers, maximum cut and minimum bisection. All right, so let's look at the limits of this maximum cut of a random regular graph. And for definiteness, let's just put expectation here, although these expressions concentrate. Okay, so let's just put expectations. This is I'm gonna call C+. And for minimum bisection, I'll do the same thing. Here, I am putting a lim-inf because this limit is actually not known to exist. So this is a technical issue. This limit is known to exist, and that was a breakthrough result, right? So the limit C+ is known to exist by this very beautiful work by Bayati, Gamarnik, and Tatali. And this uses really beautiful ideas of interpolation. You interpolate between two graphs, and you show that this quantity is subadditive, therefore it will converge. For min bisection, somehow that proof doesn't work. So we still don't know whether this limit exists. So let me just work with lim-inf. Right, so these values, we don't know what they are. They don't have any explicit expression. There is no other characterization of these values, C+ and C-, other than the formulas, other than the definitions that I just wrote down here. There is no explicit expression for these things. Okay. However, there is a very beautiful conjecture that comes from statistical physics that says if you sum them, you should get the number of edges. So here I'm dividing everything by n. So if you multiply this by n, multiply by n, multiply by n, this is the number of edges. So if you sum the maximum cuts and the minimum bisection, you should get the number of edges. Okay. So this is one of the driving conjectures in this subfield of, I guess, probabilistic combinatorics, is to try to prove something like this. So there has been a partial solution for large K of this conjecture that was established by Dembo, Montanari, and Sen. And they established the following. So if you look at large K, instead of trying to solve this for all K larger than 3, look at large degree. And this is what they prove. They prove that both of these quantities, C+ and C-, they have the following asymptotic expansion in K. The first term is trivial, is K/4. K/4 is just half the number of edges, right? So if you were to take your graph and partition it at random, take every vertex and put it in V+ or V- with probability 1/2, then the cut that you would get has expectation K/4, okay? Now, you want to maximize the cut in C+, so there is something above, so you want to increase this quantity, you want to do better than K/4, and they say that the best you can do is given by square root K. So the next order in this expansion is only of order square root K, and the constant is explicit. This is some constant P star that will explain. And then there is a lower order term. Same thing for the minimum bisection. You want to do better than K/4. The best you can do is only decrease this by a factor, by an additive thing that is of order square root K, and the constant is explicit. So that you see if you sum these two quantities, you get a K/2 plus lower order that is little o of square root K. So this is the best progress that we have towards this conjecture so far. So let me tell you what this P star is. It has an explicit formula, and you can evaluate it, and then you get this number. This is the Parisi constant, and I'll explain where this comes from a bit later in the talk. Okay. Right, so this is something I already said. This k/4 is the value of a random partition, which means that if you want to maximize the cuts, you can only do so by a an additive constant that is square root k. That's the best you can do, right? The next order term is only of order square root k. And if you're familiar with these questions about discrepancy minimization, or the things that revolve around the Komlosh conjecture, typically this is the type of order that you would expect. So the first term corresponds to about the mean, and then if you do everything randomly, and then the next order term will correspond to about something like the standard deviation if you do everything randomly. Okay, so let me explain where this constant comes from. This comes from a very different model that is called the Sherrington-Kirkpatrick model, which is somewhat of an analog to this question of maximum cuts, but on a dense graph. So let's look at a matrix A that is drawn from the Gaussian orthogonal ensemble, and this just means that up to symmetry, all the entries are Gaussian IID. Okay, the diagonal doesn't matter. You can put a variance of 2 here. It doesn't matter. And I am interested in the following problem. I want to maximize this quadratic form over all possible choices over the binary cube, plus minus 1. Okay, and I'm normalizing by 2n. So this is a problem. This is called the ground state energy of the Sherrington-Kirkpatrick model. So you can consider the problem at higher temperature, in which case you get a Boltzmann measure. But this is just the 0 temperature problem, in which case you're just looking at the ground state. And you would like to understand what the value of this is. And the value of that is exactly this P star that I wrote down. This is a theorem by Guerra, who proved the lower bound, then Telegrand later proved the upper bound for this. And you have convergence of this quantity, this random quantity, to a deterministic constant that is P star. Okay, and somehow this P star shows up in this other problem of computing maximum cut and minimum bisection. So let me show you why that's the case. So I'll just do a heuristic for a larger degree and see where we get. So let me define the cut of a certain assignment sigma to be really the number of edges that are cut, which is this, which is k/4 minus half this this product, sigma I, sigma j. So this is just the objective function that we're trying to optimize in maximum cut or minimum bisection. And let me rewrite this this particular term in the following way. So this quadratic is exactly 1/2n times sigma times the adjacency matrix of the graph times sigma. Now, this adjacency matrix is a 0, 1 matrix, but let me try to standardize it, meaning I'll subtract its mean for every entry, and I'll divide by the standard deviation, and then massage that into such an expression. So this A bar is exactly what I said. So you subtract the mean, divide by the standard deviation. So here's the expression. AG is about square root k minus 1 times A bar plus the mean, which is k/n. So for every entry, there is about probability k/n for it to be 1, because the graph has degree k, right? And the standard deviation of a Bernoulli is k/n times 1 minus k/n, n is very large, so it's just really just k/n. So I'm subtracting a 1 here, but that doesn't matter. That's just for aesthetic reasons. K is large, or k minus 1 and k are the same thing. Okay. Then the rest of it is given here. So this term, you subtract it and you add it up. But then when you add it up here, then you get just the sum of the spins squared. Okay, so this is just a simple thing you can do. Now, if I think of my k being very large, the degree of the graph is very large, and n is even larger. So let n go to infinity first, and then k to go to infinity. Then you can somehow replace this matrix A bar by a dense matrix, which is GOE, which is just Gaussian. So this is, you can expect some kind of central limit theorem to kick in, and you can replace A bar by a GOE matrix. So this A bar became GOE. On the other hand, so what I'm going to expect is that my optimal partition in the max cut problem to be balanced, meaning that the sum is about square root n. So you would expect that when you sum the assignments or the difference between the size of v plus and v minus, it should be of lower order. In particular, it should be of lower of order square root n. So this is for max cuts, but for min bisection, you already constrain them to be of size exactly the same, n over 2. In which case, this will be exactly 0, so we don't have to make an assumption or anything about this, right? But for max cut, we still expect that the optimal partition is of this order. It's balanced with deviation fluctuations of order square root, and that's not proven. That's not known to be true, actually. But if you do these two assumptions, then you get that the max cut value is k over 4, right? Then this number here, k minus 1 square root k minus 1 over 2, then take this n that divides this quadratic, then that gives you the optimization problem that shows up in the Sheraton-Kirkpatrick model. So this is the ground state value plus some error where, I'm hiding a bunch of stuff here in this error that justifies these two heuristics, right? So this converges to P star, in which case you get the value, you get the theorem that those guys have proved, k over 4 plus this much times P star, okay? So here I'm just relying on a central limit theorem. So that's the heuristic derivation. They don't do the proof like this. The proof goes through another route by interpolation with a model that is a bit more complicated, but this is basically the idea. Okay, please stop me if I need to explain anything more. So let me talk about the main results of this paper that we have with Andrea and Mark. So there exists an L local algorithm. It's randomized, such that for any graph that is L, let's say 0, 0, locally tree-like, this 0 doesn't matter. This is just for simplifying the exposition in this talk, but you can put an epsilon here. So here, this particular graph that is L, 0, locally tree-like, it means it has girth L, right? This algorithm outputs a sigma alg. So this is an assignment that is output by the algorithm such that the cut, so if you care about max cut, you care about maximizing this. The cut that you get is about the maximal value, well, the ground state value that is achieved for a random regular graph, okay? So on a random regular graph, you're approximately optimal. And as you increase the locality parameter, then you get better and better in terms of this constant. And for the min bisection problem, you just put a minus here. It's the same thing, okay? And you have an error that is of order or lower order than square root k, and then in n. So you have to let n go to infinity first. This is the size of the graph, and then let k to go infinity second. Then you get the expansion that you would otherwise get just for the ground truth value, the maximal cut value. Okay. If you put an epsilon here, then you would have to prune the graph, remove the vertices, the problematic vertices around which you cannot find a ball that is isomorphic to a tree, but then you don't pay much. You pay a factor or an additive epsilon here. Okay. Okay, so what is this star? This star is under a certain assumption. So this result is conditional. And it's conditional on the following thing, and conditional on this assumption that is called the no overlap gap property for the Parisi formula. Okay, so this is some mathematical physics conjecture that is not proven yet. And I'll try perhaps I'll try to explain what this is perhaps in the next slide or 2 slides from now. But let me first talk about the consequences of this result under this assumption that this algorithm is nearly optimal for random regular graphs because that's the ground state value, that's the ground truth value that for these 2 cuts, and you approximate it, right? But this algorithm is also kind of the best local algorithm, because if I give you a locally tree-like graph and you're algorithm is local, then it doesn't see cycles. So you might as well be on a random regular graph, right? And the value that your algorithm will output cannot be better than the ground state value on a random regular graph, in which case this is the best local algorithm if you ignore the errors. You can perhaps do better error bounds, but yeah, if you just care about the first two terms, that this is the best thing you can do. The third point is that maximum cut. So if you think about designing a graph that has the minimum max cut value, okay, you're allowed to change your graph and think about designing a graph that has the minimum max cut value, or conversely, you want to maximize the minimum bisection value. Well, that's among all locally tree-like regular graphs of the same degree, random graphs are the ones that extremize this quantity, right? Because of this result. So this is kind of similar to the Ramanujan property for random regular graph. If you just think about the second eigenvalue of a graph, right? So there is this bound by Alon and Bopana that says that for any sequence of graphs of degree k, the second eigenvalue of this graph has to be at least 2 square root k minus 1 minus some epsilon, where this epsilon goes to 0 as n goes to infinity, right? And the converse bounds, if the graph satisfies the converse bound, which means that the second eigenvalue is bounded from above by 2 square root k minus 1, it is called Ramanujan, right? And there was an open problem for a long time whether these things exist or not outside of number theory, and it's been proven that they exist. But you can also look at the performance of a random regular graph and see whether they satisfy this inequality or not. Well, they don't satisfy this inequality per se. They satisfy something that is slightly worse, and it's only worse by a little O of n. Right? So for a random regular graph with high probability, you have this bound. So these graphs are called nearly Ramanujan. And this, you can see this third property as being saying something like that, but not for the second eigenvalue. It's saying it's for these combinatorial quantities, which are the minimum bisection and the maximum cuts. Okay. No, I didn't want to do that. Okay, so let me now tell you about the Parisi formula and what this overlap gap property is. So the Parisi formula is an PDE, is a certain variational problem that involves PDEs. It's nonlinear PDEs. So this constant P star, that is the ground state value for the Sherrington-Kirkpatrick model, you can write it as a more complicated thing. It's the infimum over all functions U that belong to this class of a certain functional P of gamma. So this class of functions over which you're minimizing is the class of functions from the interval 0, 1 to R plus. They're all non-decreasing and they're L1. Okay, so there is a formula, an explicit formula that involves PDEs for this P of gamma, but I don't need it. So let me just think of this as an abstract functional, okay? But it does come from PDEs. So let me just skip this slide. Okay, so you want to minimize this functional over this class of functions. And there is a very nice result that tells you that this functional P is strictly convex over the class U, script U, which means that the minimizer has the P has a unique minimizer in this class. And now we're just going to think about whether this minimizer is in the interior of U or is on the boundary. So the no overlap property says that it's in the interior. It's strictly increasing. So you're minimizing over functions that are non-decreasing. And if it is strictly increasing, meaning that it's in the interior, you're going to say that there's no overlap gap. So this is what it's expected for the Sherrington-Kirkpatrick model. This is what the optimal gamma looks like. And if you put it in a computer and you solve it, you indeed see a picture that looks like this. But we cannot rule out mathematically that the picture will look like this. Okay, so in this case, there is an overlap gap. in particular between these 2 points. I did not explain the physical meaning of this, but perhaps you can ask me later after the talk if you're interested. So mathematically, we do not know how to show that this is not the case. And perhaps this is a side note, is that the pressures, so there are many problems that have this kind of structure. So you look at a certain variational problem that encodes the ground state energy, and if the order parameter, as it is called in mathematical physics, has an overlap gap, that means that the problem is hard algorithmically. So you can show that certain class of algorithms that are called stable will not find a solution that is optimal if you're in this picture, okay? So perhaps there's a large literature on this. Let me not talk about this too much unless you're interested. So that was the condition of no overlap gap. That's what it means. Okay, so if there are no questions around here, now I'll talk about the class of algorithms that actually achieves this bound. That is the main algorithm, the main result. Okay, so perhaps you all know what a local algorithm is, but let me just remind you, a local algorithm, we're gonna say that it's L local if it has the following structure. So you draw a bunch of labels, IID, on the vertices. These labels can be an abstract random variables, but let's just take them being Gaussian, they're IID. And for every vertex I, you output a sigma I, this is plus or minus 1 sign. That is a function of the ball around that vertex of radius L, and then the labels of those vertices, right? So this is the Marx ball of radius L. And you want this function to be deterministic, and you want it to be the same. So we don't change your function when you move from vertex to vertex. So you want this thing to be, you know, invariant under the group of automorphisms. Right? So this is what a local algorithm is. And a special class of local algorithms are called message passing algorithms. And these algorithms associate a message from any vertex I to a neighbor of it, that is J. Okay, so for every directed edge, we're going to have a message U I to J. And nodes will exchange messages. And after a certain number of iterations, you just look at the messages that a certain node gathered, and you do something with them. You apply a function to those messages, and that gives you a local algorithm, right? All right, so let me tell you what the specific update rule is in this class that I'm considering. Okay, so at time t+1, how do you update the message that comes from I and goes to J? So I look at all its neighbors that are not J. I think I have a drawing here, yeah. So I wants to send a message to J. Then it looks at all the incoming messages from its other neighbors that are not I. Then it does something with them, and then it sends that message to J. Okay, so what is that something? That something is you look at those messages, which are this, then you multiply them by some function of the previous messages up to time t-1. So this function can be arbitrary, but this is a necessary thing. I will need this kind of generality. I mean, the usual thing will not involve this. Like if you look at message passing algorithms in the literature, they typically assume that this is a constant or some deterministic sequence of coefficients. But I'm going to need this coefficients to depend on the history, on the past history, okay, up to time t-1. Then, so this is the edge iterates. Then I'm going to look at the vertex iterates. I'm going to look at all the vertices that have been sent to I at time t, and I'm going to sum over them and multiply by the same coefficients, okay? And I'm going to initialize randomly. So all these messages are initialized with IID labels. Okay. Yeah, stop me or perhaps give you some time to digest this notation. Okay, so what do I do with these guys, with these UIs? I'm going to construct a stochastic process that I'm going to call Z. And the stochastic process, so this is, it depends on time. And it's constructed in the following way. So it takes these messages and it sums them together. Okay, so these node, not messages, these node iterates, it takes them at any nodes and it sums them together across time. So across the number of iterations, right? And here as well, I'm gonna multiply by coefficients that depend on the history. They're not constant. So perhaps I'll give you a special case here to perhaps ground the intuition. Okay, and my algorithm will output these numbers. Will output these random variables for some large number of iterations. Okay, so this is what the algorithm does. Now, the freedom that you have in tuning this algorithm is choosing what A's are, what these functions A are of the history, and the B's. So this is what you can do. You just choose them in a certain way that fixes the algorithm. Okay. So perhaps it's not hard to convince you that this algorithm is T-local because I just did T steps, capital T steps in this process. So it's T-local, right? And this class of algorithms generalize a few approaches that we know of. In particular, there's a result by Russ Lyons that give an approximation to the maximum cut value by a factor of 2 over pi. And the algorithm, it is, okay, so it is not written as an algorithm in Lyons's paper. It's written as a block factor of IID, but it's approximable. This block factor of IID process, you can approximate it by an algorithm, and this is the way to approximate it. And this is a very simple choice of these functions, of the functions that depend on the history. So I'm just going to choose the capital A's to be all 1. So there is just coefficient 1 that doesn't depend on anything. And the B's, I'm going to choose them deterministically. They don't depend on the vertex, the specific vertex. They only depend on time. Okay, delta is 1. So let me go back. So these B's do not depend on a specific vertex. They only depend on time, and they're fixed, deterministic. So yeah, this function is trivial. And these A's are 1. So this A and this A are 1. Okay. So in effect, I'm just looking at the messages that V sends to I. I'm summing them together, and I'm going to send that to J. Okay. Okay, so one thing that I need to do is to choose these betas. So these coefficients, I'm going to choose them in a certain way. So I'm going to gather these coefficients beta in this vector that is T-dimensional. I want it to be an eigenvector of the following matrix, the matrix that has above and below diagonal B1. That's it. Okay. Everything else is 0. And these matrices have eigenvalues that are between -2 and 2, so you can work that out. So in particular, if I do these choices of the A's and the B's and the delta, then UIL, so after L iterations, my UI will only depend on the labels of the vertices that are distance L from I. Perhaps I should draw some picture here. This is I. And these are concentric balls or concentric radius of increasing radius. What you're doing here is looking at all the labels of the vertices at a fixed radius. You're summing them together and you're sending them to I. And for a larger L, you're looking at all the vertices, all the labels of these vertices, you're summing them and then you're sending them to I, okay? So I, after a certain number of iterations, it has this sequence of numbers that are obtained in this way. So take that sequence and weigh it by some coefficients beta, okay? And you sum them. Take a linear combination of those messages and sum them. So, okay, so you see that these are Gaussians, right? because every guy here is Gaussian. So these are Gaussians. And I'm taking a sequence of IID Gaussian, they're independent because I'm changing the distance, right? These are a sequence, these are a sequence of IID Gaussians as you change L. And I'm taking them and I'm taking the linear combination of them. Okay. So let me now take an edge ij and compute the correlation between z sub I and z sub j if I construct z in this way. So a simple computation using these formulas will get you that that's square root k minus 1 over k times beta t beta, where t is this matrix. Okay. Now you can choose beta to maximize this quadratic form. In particular, if you choose it to be just an eigenvalue of some eigenvector of some eigenvalue rho, then you get this value. Okay. Now the result of Russell-Lyons just says, okay, take rho to be +2 or -2 if you, depending on whether you care about max cut or mean bisection. Okay. By the way, this is a Gaussian process, right? The way we constructed it is a Gaussian process. And this is what's called the Gaussian wave function, right? So this is a construction of the Gaussian wave function by these people. Okay. So I did it on a finite graph, but you can do it on the infinite tree. That's the same thing. You can let the t, the capital T here, let it go to +infinity, right? And this is one definition of the Gaussian wave function of this with this eigenvalue. Okay. So in particular, if the tree, well, we know that the tree, the k irregular tree has radius 2 square root k minus 1. In which case, if you want to construct a Gaussian wave function with that eigenvalue, you just take the rho that corresponds to the eigenvalue 2. Right, so yeah, what is the result of Russ? Or -2, I guess, if you care about the maximum cut. Take rho to be -2. And then constructs this Gaussian wave function, zi. Then threshold it, take the sign of that. Now the cuts that you achieve using this construction gives you a k/4, which is the trivial thing. Then you get the square root k minus 1, so this is good, right? The next order term is square root k. And you get a constant in front that is square root, that is 2 over pi. Okay, that is given by this sign thing. So yeah, if you take probably that sigma I and sigma j have the same sign, sigma I equals sigma j, is given by the probability that the product of zi times zj is positive, and that gives an arc sign, whatever. And then when k is large, then that gives you 2 over pi. There's some trigonometry going on here. Okay. The result that I promised you is p star is not 2 over pi. And if you evaluate these numbers, they're not the same, right? So we improve over the result of Russell-Lyons and we get the actual number, which is 0.76. Okay. Okay, so how do we improve over it? Well, we have just to really choose those functions in a smart way. So instead of constructing, instead of taking these labels at concentric radii and then just summing them, so sum these and then sum the whole thing as a linear combination, you're going to have to do something a little bit more tricky, a little bit more sophisticated. You're going to have to construct a martingale. So a martingale that's right, so it's not the sum of IIDs, it's not a sum of IID random variables. Each random variable in that sum can depend on the previous history, on the past, in which case it becomes a martingale. Okay, so this martingale is built on every vertex, right? So it's a stochastic process that evolves over time, and it's indexed by the vertices of the graph. And for any neighboring vertices, sorry about that, for any neighboring vertices I and j, these two martingales zi and zj are correlated in some non-trivial way. Okay, so these have to be coupled in a non-trivial way. So that's the following two things happen. I want zi as t goes to infinity to converge to plus minus one almost surely, because my spins, I want them to be plus or minus one, right? At the end, I want to be sure whether to put a vertex on this side of the partition or this side of the partition. The other thing I want the correlation to be maximal. So if I care about maximum cut, I want this correlation to be minimal, right? So with the minus, it's going to be negative. I want the correlation between two neighboring vertices to be negative, right? So if I put this guy on one side of the partition, I want to put its neighbor on the other side of the partition. So I want this to be negative and very negative. If I care about minimum bisection, I want to put them both in the same side, on the same side of the partition, in which case I want this to be positive and very, very large, well, close to one. Okay. So I want the absolute value to be maximal, depending on whether you care about minimum bisection or maximum cuts. You remove the absolute value and you put a minus. So this is my I want to construct a factor of IID that satisfies these two properties. So the first thing that you can ask is, what is the max? If I give you a factor of IID on a tree, what is the maximum correlation that you can hope for, right? Suppose that the variance of each one of these zi's is bounded by 1. And then I can ask you, maximize this correlation or minimize it, given or over all processes on the tree, which are factors of IID. Okay, so there's something that is not very hard to prove, is the following. If you have a factor of IID on the tree, mean 0, variance 1, then the correlation is always bounded by this number, 2 square root k minus 1 over k. So you see, this is related to, well, you'll see that this is related to the radius of the tree. This 2 square root k minus 1 is exactly the radius of the tree, spectral radius of the tree. And the way to prove this is to approximate the tree by a random regular graph. So this graph will converge to the tree in the weak topology. But once you restrict to a small graph, to a finite graph, that you can use results that are known for these finite graphs. In particular, for a random regular graph, Friedman's theorem tells you that the second eigenvalue, and this is something that I already talked about, the second eigenvalue of G and K is bounded by 2 square root k minus 1 plus some little o of 1. So if you use these two facts, then you get the answer here. So I think I still have a little bit of time to show you how the proof works. So let me try to do that. So if you approximate the graph by G and K, and think of the girth of the graph G and K to be at least L or 2L perhaps. So you sample a graph that has this property, and you know by Friedman's theorem that the second eigenvalue of G and K is smaller than this much, right? So plus little o of n. Now look at a L-local algorithm or a stochastic process Zi that is a block factor of IID or a local with the parameter locality parameter at most L, right? In which case the algorithm only sees a tree. Around every vertex, it only sees a tree. It doesn't see the cycles. So you might as well be on T. You might as well be on the infinite tree. It doesn't change anything, right? So the expectation of Zi times Zj, well, it's the same thing as, so this is for an edge, right? So this is the same thing as, adding all the edges, adding this quantity over all the edges and dividing by the number of edges, which is exactly n times k times the expectation of z as a vector, times the adjacency matrix of the graph times z, right? Now, this is the adjacency matrix of the graph. I can do the following. I can do the standardization trick that I showed you earlier. So I can subtract the mean of every entry. So this is the all ones matrix. And add it back. So I get, if I add it back, I get 1z squared expectation 1 over n squared k, something like this, I think. Now, if I subtract, this is the first eigenvector, which is 1, right? Now, if I do triangle inequality, not a triangle inequality, but Cauchy-Schwarz, I get lambda 2 of AG multiplied by the covariance matrix of Z. So this is the covariance matrix of Z, plus the other term. But this thing, what is this thing? Z is L local, and I am summing over all the vertices of the graph. But since it's L local, typically 2 vertices are going to be very far apart from each other, in which case they're going to be independent. They're going to be, a distance at least 2L. If they're a distance at least 2L, they're independent, in which case this expectation vanishes. So all in all, this will be 1 over n squared k times some constant that depends on L times n, right? It's not n squared, it's n because it's L local, right? So this thing goes away. So n over n squared, this thing goes away. So let me just remove it. Right? Covariance, why am I doing covariance here? This thing is trace of the covariance. This is a matrix. So this doesn't type check. This is the trace of the covariance. Okay. Well, the trace of the covariance is bounded by 1 times n, right? So every entry here has variance at most 1. So the trace is bounded by n. And the second eigenvalue is bounded by this. So this is bounded by 1 over nk times 2 square root k minus 1 times n, right? So that gives you the answer. So there's a generalization of this results that not only cares about correlations for neighboring vertices, but it cares about correlations between vertices at distance L. And then you get a corresponding bound that is not this one, but there is a bound that is proven by Virag and collaborators. So this is a special case of that. Okay. So this is the best you can achieve. This is the best correlation you can achieve for a factor of IID on a tree, right? But you may perhaps remark that this construction, Lyons' construction, achieves this bound. So what's the problem, right? Lyons' construction, so the construction that actually achieves this bound is the Gaussian wave function, right? So if Z is a Gaussian wave function, then it's exactly is this number, right? So you have one of these bullets which is satisfied. This is indeed maximal, but it's not plus minus 1. It's a Gaussian. It's not plus minus 1. So if you want plus minus 1 out of a Gaussian, one way to do it is to take the sign. But then when you take the sign of these guys, suppose that this is the Gaussian wave function, you take the sign coordinate-wise of that stochastic process, you get a new stochastic process which now satisfies this bound, satisfies this condition. But this is no longer maximal, right? Because you took the sign, right? So these are Gaussians. They're not plus minus 1. But then if you take their sign, then they become plus minus 1, but they're no longer maximally correlated. So you want both. So you want to maximize this over all factors of IID that are also binary. So this is the problem. So here we're going to import the solution from the solutions from the SK model, from what we know about the SK model, and this only works for a large degree. It doesn't work for like degree 3. Only works asymptotically. Okay. So perhaps I should explain something about the SK model that we now know, and this has been a picture that has been advanced by physicists, in particular Giorgio Parisi. And this is about the organization of solutions to this optimization problem. So if you look at all the maximizers or the near maximizers of this quadratic form on the cube, And think of that as a metric space. So you have a certain number of points, and think of that as a metric space. What is the L2 distance between any 2 points? Turns out that it's an ultrametric space. It's a tree space. It has the topology of a tree, or the metric properties of a tree. And this tree can be represented in the following way. So you can index it by time from 0 to 1. 0 is the root of the tree. 1 are the leaves of the tree. This is almost a continuum tree. So it's a discretization of a continuum tree. The internal nodes of this tree are physical points in the solid cube. And these are the barycenters of the leaves they generate, of the children they generate. So if you look at this point MT, you look at the points that they generate, the offsprings of this point of this MT. Those are also points inside the cube. And if you take those points and you average them together with a certain weights, with a certain family of weights, you get MT. And that happens recursively up to the point where you reach the actual leaves of this tree, which are indexed by time 1. And these guys, so the leaves are approximate optimizers. Turns out there's more to say about this picture, but okay, we don't need to go there. Like these, like along every path here, a certain function that is called the tap free energy is conserved. It's always constant. There are many properties that you can say about this. And one way to optimize now, one way to solve this optimization problem, and this is something that has been done in this sequence of works in increase in generality, is to find an algorithmic way to explore, to construct this path in the tree. So try to explore a random path in the tree algorithmically. And you know that if you follow one of the branches approximately, you're going to reach a point that is an approximate optimizer. So there's a literature on these things in probability theory. And we're going to try to import this technology to solve the problem in the sparse case, on these graphs, on random regular graphs. One thing that perhaps is going to be useful to us is that this MT, when you look at it as a stochastic process that is indexed by time from 0 to 1, the law of this stochastic process is very well understood, and it follows from the Parisi formula. And what we're going to do, we're going to try to simulate the law of this thing, of these M's, to construct our Z's, to construct the stochastic process that are the Z's. Excuse me. Okay, so we're going to choose these nonlinearities, A and B, capital A and capital B, so that Zi for any fixed vertex I as a function of time, so this is a stochastic process, I want you to approximately have the law of this MT. Okay? So this MT is inside the cube. In particular, each coordinate is between -1 and 1. At time 0, it's at 0. At time 1, it's at 1. So it does converge when time goes to infinity, or goes to 1, depending on time parameterization. This thing will happen. So the first bullet here will happen. As time grows, I will converge to a point in the cube. It's plus or minus 1. Right? Just because of this construction, this tree hierarchy that shows up in the SK model. And now if I look at the correlation between Zi and Zj for two vertices I and j, which are neighbors to each other, then you can write that as, so this is just for one edge, but you can add, again, sum over all edges and divide by the number of edges. And that gives you the quadratic form that you have to optimize for the SK model, right? So this is what I did here. Let me go back. This is what I did here. If we look at the correlation between Zi and Zj, I divided by the edges and I summed over all edges. In particular, this is the adjacency matrix of the graph. And now I don't do this, these inequalities. Now I just look at this. And I use the interpolation arguments that is used by Dembo and Montanari. In particular, I know that this is close to P star, right? So perhaps I can write it. Okay, let me remove this line. So this is the adjacency matrix of the graph, and I want to show that this is close to P star modulo these the square root k over -1 over k, right? So I can do the same thing. So I can subtract the mean of these entries and add them back, but this term will go away because my process is a factor of IID, is a local block factor of IID. This goes away, and you can approximate this by a GOE matrix, right? So this is about 1 over mk times square root k minus 1, then divides this thing by square root k minus 1. This is a GOE matrix. So this is about the expectation of Z GOE Z. Then you know that this is about P star, right? If I choose these guys correctly, this is about P star. So what I get is this correlation is about P star with a plus or minus, depending on whether you care about minimum bisection or maximum cuts. Okay. So you see that this argument only works when k is large, because I did this approximation of the matrix, of the adjacency matrix of the graph by a GOE matrix. And that only happens, that approximation is only accurate for k large, right? So this argument does not work for k equals 3 or 4. Okay. So let me wrap up. I think I'm slightly over time. The solution here is somewhat ad hoc because we know how to solve the SK model. Then we just imported that solution to the tree or the graph. But one question that could be asked is whether this could be solved more systematically. If suppose you don't know about the SK model or anything, can you solve this in a more principled, systematic way? One other thing is algorithms that work for any k that is not large. In particular, I have this question, which could be interesting. If you take the maximum cuts at any k, subtract the trivial value, k over 4, and divide by square root k minus 1. So this is supposed to be P star if k is large, right? But now as a function of k, you can ask whether this is decreasing. So whether it decreases to P star. So this is P star, this is k. And whether this quantity is decreasing towards P star. Seems like in simulation, it looks like that's the case, but we don't know how to prove it. And in which case, that means that for every fixed k, let's say k equals 3, that is here, you know that the maximum cut value is larger than the equivalent of the problem, the maximum cut value for very large k. And we now have an algorithm that solves the problem and gives you a P star. So we can ask whether for any k you can get the P star. You can get this value. Is this true for any k, for instance? Not for k large, but remove this O, whether this is true for k larger than 3. And you can construct a factor of IID that satisfies this. All right, so if this is not true, or more generally, I guess, the more general question is to construct a maximally correlated binary valued factor of IID on the tree for any k larger than 3. So this is something that we don't know how to do. And it'll be really cool to find a way to construct them. Okay, so let me stop here. Thank you very much. I've already took too much of your time.
Thank you.
Yeah, thanks.